Okay, so I'm going to talk about fluid pressure against vertical plates. So when we talk about fluid pressure, you could have fluid force on a constant depth surface, and that's just this like nice formula. So it's the same depth all around. And where integration comes into play is if you have a vertical plate, because with a vertical plate submerged in water, the deeper this vertical plate goes, the more pressure that will be on the plate. So there's a varied amount of pressure. So because of that, we need an integral. And this is actually pretty straightforward. I think that these problems are some of the easier ones to interpret because it's the same formula. So you just have to kind of know like how to break down the problem. So this A to B, you just want to pay attention to where the plate is actually running. So pay attention to your coordinates. W is weight density, and this is almost always going to be 62.4, at least in the problems that I'm working with. And then L of Y, so this is the length of a horizontal strip measured from left to right. So this is again going to be in the context of the problem. So sometimes this could be a curve. So I'll show you how to calculate that. Now, one thing I want to say is just the weight density of fresh water that I'm going to use over and over again is 62.4. So we can just take that number for granted, even though I never say it's fresh water. We can just take it for granted. Okay, so let's calculate the fluid force on one of the triangular plates using the given coordinates. So I'm given this situation here, okay? So this has been pre-labeled for me. So now all I have to do with this is interpret. So notice in the coordinate system that it's given, that I'm given, so my plate starts from -3 to 0. I've got my start and my end. So these are my limits of integration. Okay, so the strip depth is very simple to find because what you have to do is you just have to know where the pool surface is. And so then your strip depth will be somewhere on this part here underneath the pool surface. So my strip depth is just going to be 1 minus y. Okay, the next thing I've got to figure out is I've got to figure out this equation here. This was not given to me, but I can figure out some points just looking at this. So I've got the point 0, -3, and then 3, 3, 0. So I can just use some algebra to figure this out, right? So this is y-intercept of -3, and then obviously I'm going up 1 over 1 for my slope. So this equation right here is y equals -3 plus x. And so the only thing with this is that this is an equation written in terms of x. So when we do these types of integrals, we're always integrating with respect to y. So now I just want to rewrite this equation as 3 plus y. So I solve for x, okay? So I am going to note that right there. So that part's there. Okay, and I need to know what the equation of one side of the plate is so that I can get the next part of this, of my ly. So my ly is going to be something that varies. So I drew, let's see, I'll draw a couple of these here so that you can see. So I drew one line here. So I need some way to represent, so let me draw like a couple more lines. So let's say I've got like this line here and this line here. So I need a formula that captures the length of these different lines. So these lines are dynamically changing based on how far I am down this curve. And I know what this curve is. So this curve and this curve, we can assume that these are running symmetric. So the length from here to here, that's whatever this x coordinate is. So that's 3 plus y. So if this length, so maybe I'll say from here to here, if this blue length from here to here is 3 plus y, then to double that, I just take 2 times 3 plus y. So there is how I find my L of y. So you just have to know what this curve is and then just figure out like what's appropriate as far as getting like this entire length as it varies. If it varies, it doesn't always have to vary. Okay, so again, we just want to assume the weight density is 62.4, and then I'm just going to plug everything into this formula. So now it just comes together quite nicely. So I've got my 62.4, I've got my strip depth, and then I've got my L of y. Bada bing, bada boom. Now you can go ahead and you can integrate. Now, the one thing I do want to point out with this, maybe I'll come back here for a second, is so notice, so based on this coordinate system, this is where my plate started at -3, and this is where the top of it was. So I need like some way to orient this. In this case, it was given to me, so that's what I used. If it's not given to you, then you can set the coordinate system, but in this case, it was handed to us. Okay, so here's what I want to integrate. So let's see, I can multiply this 62.4 and the 2, and I can bring that out as a constant, and then I can go ahead and I can just FOIL the rest of this. So I get the result that you see here, and then I can go ahead and just plug everything in. So this is my final answer. So I'm assuming that you know how to do the integration, so I'm going to just kind of fast forward through that, and you can pause the video if you'd like. Okay, so now let's flip this a little. So in a pool filled with water to a depth of 12 feet, calculate the fluid force on one side of a 4 foot by 6 foot rectangular plate if the plate rests vertically at the bottom of the pool on its 4-foot edge. Okay, so in this case, I don't have a picture, so I just have to orient myself. So I'm told that the pool is 12 feet. So we'll assume here's 12 feet, and then here's where my plate is. So I'm told that the bottom of the plate is the 4-foot edge. So this is like a good enough approximation. And okay, so the strip depth is just going to be the 12 minus y. And then, okay, so remember, the other thing I have to figure out is this length here. Now, in this example, this length does not vary, right? All the way up, it's just a rectangle. So the length doesn't vary. So all I have to do in this case then is just state what is this length. It never varies. It's just always 4. That was a given in the problem. Okay, so I've got all of that. The last thing I can do here is I can set what my coordinate system should be. So I'm going to say that this is the bottom, 0 to 4. You can just set the coordinate system if it's not given to you. So that's how I'm going to, oh, sorry, not 0 to 4, 0 to 6, my bad. Okay, so I go from there to 6. Okay, so now I've got all the pieces that I need to finish this. So the bottom of my plate was here at 4. The top of my plate is going to be from 0 to 6. So if I just plug everything in, okay, so there's my freshwater density, strip depth, and then there was the length of the bottom edge of the plate. Okay, and so now I can just multiply all this together. So if I take the 4 times the 62.4, I can pull out the constant. So here's all I've got to integrate, and I'll just show you the rest of the work. So after I plug everything in, I get the answer that you see here. So once again, you can always pause the video if you just want to check your work against mine. Okay, and so that brings us to the end of this video, just a short and sweet one with a couple of examples. So I will see you guys next time.